world where space and time are intertwined, one man dared to challenge the status quo. His name? Dayton Miller. His weapon of choice? A flute. But not just any flute. This instrument held the power to unleash the ether, a pervasive medium once thought to fill the universe. Miller, a physicist by trade, a musician at heart, discovered a harmonic resonance within the ether. He found that his flute, when played with precision, could manipulate this elusive medium. His melodies, a symphony of science, had the potential to shift the very fabric of reality. However, a sinister force lurked in the shadows. The Einsteinian demons. These creatures thrived in the distortion of space-time, causing chaos and disruption. The world needed a hero, and Miller was ready to answer the call. With his flute in hand, Miller played a tune that echoed through the cosmos. Each note, a shot of pure ether, struck the Einsteinian demons, dispelling them back into the void. The world was saved, not by a warrior, but by a musician, a scientist, a man with a flute. Remember, in this universe of wonder and mystery, sometimes the most unlikely heroes make the biggest impact. Keep your mind open, your heart brave.
You posted an ether cause?
All right, hello and welcome everyone to Celestial Theodolite update number 30. Today we're going to go over a little bit of central angle theorem, and then we'll touch on virtual images at the end as a follow-up to last week's conversation. So, as Beast was just laying out earlier before we came on, there's a geocentric position that is referenced for the positions of stars to relate them to a ground position. And this is done by tying the 60 nautical mile per degree relationship to a 15 degree per hour angular descent. Now, if those two things are true, then that star's ground position referenced on the first point of Aries at a zenith will then also be true as you calculate it out throughout the any time after that. So with that, but there's a certain angular band in which that linear relationship holds true, and it's about when the star is at 30 to 70 degrees or so, it seems to follow the 15 degree per hour relationship really well with the position that we do see. But as the star gets lower in the horizon, they start to have to introduce atmospheric refraction corrections that are a specific amount that tie it to the 15 degree per hour position, so that no matter where you see that star apparently, it'll be tied to that ground position at the 15 degree per hour rate. So that's how they link it all together. And I have a citation here from the Nautical Almanac, from the explanatory supplement to the Astronomical Ephemeris and the American Ephemeris and the Nautical Almanac. So basically a bunch of people were asking, hey, how do you come up with these corrections and stuff that you put out for the almanacs and every year and whatnot? So the British Crown put out this book to, tell the tale of how they how they use the ellipsoid model in these geocentric positions to calculate everything, to verify their positions. And then they give a reference for how astronomic refraction is handled. So I went through these citations here, and in another Prezi that I did, I went over some of the citations and what they do. And all these are their expansion series where they're integrating data and observations into what it needs to be to maintain the 15 degree per hour relationship. Because as they get really low in the horizon, like, sub 10 degrees, sub 5 degrees, etc., they start to really not follow the 15 degree per hour relationship. So that's where they start to introduce specific amounts of refraction. So like when you're looking at this example here, North Peak in Colorado, which is 2,000 feet above sea level, there's a 23 Archimedean astronomic refraction correction, and that's because the star's true position, the one that's following the 15 degrees per hour, is geometrically below the peak, but they're saying that it's refracted up by 12 arc minutes, and then another 12 arc minutes to put it at its apparent position for the observer there. So whatever refraction amount has to be for you to see the star, that's how much is going to be calculated at the time, and that all comes out of these formulaic computation things that are based on assuming multiple basically they model out a static homogeneous gradient assuming Earth's radius, and then they build it out outwards from there so that it's all symmetrical and bends light such that it'll always be exactly to maintain the 60 nautical mile per degree relationship. So that's how all of that is referenced. But what Beast was touching on was something that I noticed last week when I was going through it. Let's start with Pikes Peak before we go anywhere else, because that's the familiar territory, to make sure everything is calibrated correctly. So let's see. We're going to cover central angle really quick. So this is what central angle looks like if we have an observer here and we have some distance away here defined by the coordinate system. This is what it would look like. So the distance between them would be a angular an angular measurement, and you can transfer that into a distance by multiplying that angular amount by the distance. So we have that here in the spreadsheet. So in this case, there's 27 arc minutes between the observer Mike and the mountain peak. Now on both models, there's a mountain peak at the end of that arc length, and there's a rise over run to that peak that we're calculating, using the internally consistent system. So in terms of distance and elevation of mountain with respect to sea level, etc., we're taking that for what it is. One second, just getting some water. And then on the globe model, there's going to be a slightly smaller mountain because of drop over distance of that arc length. And if you see here, there's a mathematical relationship between gamma, which whenever you hear gamma in this context, it represents the central angle. So gamma in this case would be 27. There's a half gamma, and that half gamma represents the drop over distance of that arc length. So there's that proportional ratio there, and you can use a basic trig function to convert it from an angular amount to like a meters amount, just a tangent function, because you already have the angle and you already have the distance, so you can tangent that out to get what it would be in meters, and in this case it comes out to be 200 meters. So you just go ahead.
I'll go back to that. I just kind of want to lay it out for people. Okay, so gamma is the entire angle in terms of the arc length. So 27 arc minutes. That's gamma.
Yep. And that also
Okay.
represents the amount of celestial drop. So when Mike was calling it celestial drop, and that's actually what it's labeled in the spreadsheet, well, when the fictitious observer is referenced to describe the angular descent of a star to maintain the 15 degree per hour, 60 nautical mile per degree relationship, this gamma amount would be so like as the star moves and angularly descends in time, it's also traversing the surface of Earth. So as it traverses that arc length, it's also dropping by that amount. And then because they related to 15 degrees per hour, we based on that true position to give the usefulness of the geographic position, which is the ground position as we call it, we know how long it'll take for it to angularly descend that much. So
right, and that's between, and so when you see the two, see the surface of Earth, if you point to where the observer is on the circle, right there. So from there, that's where the observer is, and then the mountain peak is at the end of that. Boom, that is gamma. So no matter what, that star is going to decline in terms of an angle, which is gamma, and then that corresponds to a time. No matter what, boom, that's all. Those are all locked in.
Yep. And someone's hot micing
so
a
to
little
speak.
bit or echoing you or
It sounds like
something.
an echo. Yeah.
Yeah. Right. So yeah, we have our predicted amounts based on the internally consistent model, and by our internally consistent model, of course, I mean the two sphere model, the celestial and terrestrial sphere, where they have to be merged together by this transformation to the center here to establish the ground position nautical mile per degree relationship. Let's see here. Where
Maintain its
were we?
ratio is what you're saying, right?
Yeah. Yeah. So anyway, based off of the rise over run to the peak and using their 15 degree per hour angular descent coordinate system, we predict that the occlusion time for Pikes Peak will be 1843.18. Now the globe, following their geometric intersection, for their observer based position, they should predict the peak and the star true position lines up at 1842.04. And we covered that last week as well. And we're all in agreement. Now, people say that the reason that they don't occlude is because of astronomical refraction, which we'll get to in a minute. But let's continue here. But in every measurement, you'll notice that flat Earth is off on their prediction, even though we're always closer in the intersection angle. Now, when we derive an elevation based off of the occlusion angle of which is where the star's purported true position is with respect to the peak at the time of occlusion following the 15 degree per hour angular descent rate, we get this triangle, and in this case it's 30 meters off, so it's reasonably close. You don't have any reason to suspect that, like, oh, what's wrong here or whatever. But as we continue on, we notice that every single measurement is like that, and the common factor here is that and even when we go to star emergences like Old Blend and Houndstooth, they follow the same situation where the central angle relationship distance in terms of distance angle wise has to be traversed relative to the observer before the star becomes visible or gets occluded. So my hypothesis is that the true position of the star doesn't angularly descend at 15 degrees per hour relative to the observer. It actually goes at a different rate, and that's why it doesn't occlude until it hits the until it's angularly aligned with the mountain peak, because it's still following the 15 degree per hour relationship. It's just lingering for us. But there would be no way to ever know this in either model, because it's based off of the apparent position and the usefulness of the ground position. So everyone agrees that if you use the coordinate system, that it's going to be accurate and relate a position of a star to the ground and all of that based off of a true position. And we're all assuming that the true position angularly descends at that rate. But on a flat Earth, it's you're not going to have the true position actually angularly descending like that. It's going to linger. So I think that that's the difference in all of these measurements. That's why it's off, because when you reference the end of that central arc length relative to the observer, hold on one second. It occludes, at the end of the arc length, but it's always the 15 degree per hour angular descent reference that we're making is what ends up being off. And what's really interesting about that is that in every single measurement, the amount that we're off by, the intersection difference, if you add them to what the globe was off by, you get the full central angle amount. Or, I'm sorry, not the full central. You get the half gamma amount, which is proportional to
Drop over distance.
which is which is the drop over distance, but it's also proportional to the full central angle. So
Wild.
So I think like like our premise of occlusions being physical intersection based is sound, because when this physical intersection actually occurs relative to the observer, it gets occluded because there's nothing there at the end of that arc length other than a mountain, and one model had an earlier time to get theirs, one has a later time, and it ends up being a little earlier than what the later time is predicted, And I think that's due to the relation, like just the conceptual model of how the star is said to be following 15 degrees per hour isn't true. So that's my new position on that. And when we go through all the mountain peaks here, so we'll just run through these real quick. We got Blodgett Peak, 5 degrees off in position, which is going to affect the triangle because it's based off of the where it should be at that time, but it was 27 seconds, real seconds early. But again, at the end of the arc length, and over here, over here I have the arc length difference of at the time of occlusion to make sure that it matches up. Now, using that time by itself would kind of be like self-referential because we already have the time of occlusion, but the difference in our predictions is proportional to what the drop over distance should have been. So basically it like that should be reversed. If the earth was a globe, that's how much flat earth should be off, like these numbers wise. It would create
It
the
literally
exact
should be reversed.
it would create the exact mathematical opposite. And then so let's see, where was we at? Oh yeah, okay, so we go into Cheyenne.
All right, so let me see if I can steel man this. So what you're saying is the flat Earth prediction is off by the exact amount that the globe Earth predicts drop over distance based off of the 15 degrees per hour declination.
We're off by a little bit of what it is, and the globe is off by the majority of the other part of it. So the total of us makes up whatever the drop over distance is. So like
When
in
you
this
add them
case,
together.
so like in this case, if you take our intersection difference, subtract it from their intersection difference, you get 11. So you had to
That's
add it. You had
literally
to
the
add it in
half
pikes because it
gamma
was
every
negative.
time.
But yeah, when it comes out negative or whatever, you add it, and then when it's positive, you subtract them, and it always comes out to be gamma.
The only difference between the model is the Earth curves. The distance or the difference in prediction should always be proportional to the drop, right? Like, is there any other factors?
Say that again.
I'm just saying because correct me if I'm wrong, the only difference between the two models, flat and globe, is the drop over distance. So the difference between the two predictions should always be equal to the impact of that drop over distance, right?
Yeah.
Yeah, so that'll always be the difference between the two, just by definition.
Yeah, and that's what I use to verify the consistency of what we're doing in the spreadsheet and everything, because that's exactly right.
Makes sense. Okay.
So yeah, when we say that
implies
so that when we say that it should be reversed, because if the Earth were a globe, then it would be the opposite. So for the measurements for flat Earth. So as we continue here, we have 3 arc seconds off on this one. Globe was off by 17. And then another thing I want to note is earlier I talked about how they go over astronomical refraction and how it's formulaic out of all these papers that I referenced from the Nautical Almanac thing. What they end up saying is that they would like to do experiments to verify the validity of whatever, but that's just what it computationally comes out to be. And with that, I want you to note that the central angle from observer to peak, how much astronomical refraction there is over that arc length, and then specifically how on a globe, when we're looking at drop over distance relative to some arc length, how that refraction amount is like saying, okay, the star is supposed to angularly descend by this amount at this time, but because of refraction, it's actually being lifted up by half of the drop over distance of whatever arc length you're working with. And then Oh, and in almost every case, the amount of astronomical refraction exceeds the drop over distance for the arc length, and in some cases, it even exceeds the central angle, which is to say that there's
Insane.
no, which is like literally implying that there's no drop over distance. So we'll continue on to Mount Rosa, and I'll point those out as we continue. But yeah, go ahead.
The astronomical refraction is for the star, not the mountain. So, like,
Correct,
it
but
may.
Correct, but it is relative to that arc length that we're looking at. So in terms of how much lift it's going to apply over distance, it's directly translatable to that in terms because we have a defined arc length to it.
I guess you can
So
answer the two. Okay.
yeah,
Which
so
is
like
why the globe should have their star occlusions, at an earlier time.
like what we get that too, but what we can do because of that ratio where we have a defined arc length now, we can actually look at it in terms of lift. So you can convert the angular amount into meters over that distance. So over that distance, they predict 178 meters of drop for curvature, but they give 215 meters of lift for the star. So that's the kind of timing slash angular relationship that is just being regularly put out at these angles. And like I said, it's just mathematically computated to be what it has to be to maintain usefulness to the true position, regardless of whatever conditions actually exist.
Hence
Uh,
locked in.
let's see. And then we have Green Mountain here, where we were 1 arc minute off. Globe was 15 arc minutes off. And the refraction amount here is exceeds the drop over distance amount again. And it's not quite the full central angle, but it's pretty much all of it. Um, let's see here. Um, yeah, again, I just want to reiterate, at the end of this on both models is a mountain. We all agree. The only thing that's kind of in contention at this point is the angular descent of the stars, because that would be the only thing that would produce this difference. Otherwise, we'd have to argue that the elevations or sea level or something was off, and we're taking that as is for the internal consistency and whatnot. I don't think that the mountain is higher than the whatnot, but because we're referencing where the star should be in the coordinate system at the time of occlusion, that produces a different ratio for the triangle. Is that we're only starting with two of the components, and one of them, or we're only starting with one of the known variables, and the other component comes from the occlusion position. So North Peak here. Now this is one where it gets really bad for the globe, because here they say that the star is geometrically occluded by Earth curvature, but it's being lifted up by 23 arc minutes, 12 to lift it up over the ball, 12 to put it in visible range for the observer here. And it gets occluded at the end of this arc length, which is 1 degree and 10 arc minutes. This is the longest distance one we've had, which is the largest discrepancy, or one of the largest discrepancies for the angular descent position, because that's what's going to dictate that, at the time of occlusion, where that physical light source intersected the mountain peak. Because that's like if it's 14 arc seconds, like it had to. This is why it occluded early, because it's not following that angular descent rate. There's nothing else, because there's a mountain there, and there's a star's true position that's supposed to be in this spot. So the fact that it happens early at the end of that arc length, I mean, it seems to me it's pretty straightforward, but I can understand if people aren't going to agree to that or whatever. But that is my current
I see
interpretation
what
of
you're
it.
saying, though. I see what you're saying. So basically, the fact that it includes earlier shows that the star is not actually declining or yeah, declining as if it was going beneath your feet in a sense, because Earth rotation, that's why the stars are moving, etc. So Therefore, it would have to decline if we were on a ball. The simple fact that it got occluded earlier means that the star is still above head, just farther away, essentially.
Yeah, because they already were under the ball, and then it gets occluded with like 2 arc minutes over what they would geometrically predict. So it doesn't even make sense on a globe.
No shit.
Well, I mean, 2 minutes still. We went into this last week. I don't need to go too deep, but 2 minutes is a lot less than 14.
No, but you don't understand. It's 2 minutes of a refraction amount that can't be ended early. There has to be that much refraction to make the GP useful in the model. And if there is that much refraction, then it can't occlude 2 arc minutes in difference. So like that was the whole point of going over that, because these amounts are saying that they're geometrically over the peak for the globe at the time. So how would that cause an occlusion if there was no mountain there and the star was 11 arc minutes under the globe, you know, and it's still visible by 12 arc minutes? There's you would, as much refraction as was needed to explain the observation is how much you would say is there. But in this case, there's a mountain, and that refraction amount has to always be cut short in every single scenario to match the occlusion time, which is the rise over run to the peak, but just not following the model's 15 degree per hour angular descent relative to the fictitious observer.
Okay, but use the same standards for the flat prediction.
We are. That's why we derive
That's what it
That's
is
why we
right there.
derive triangles. We're looking at the difference in the elevation of the star relative to the observer between conceptual model and reality. Because there's nothing else here to occlude this other than a true position of a star where it's out of position. It's not. The globe lads wouldn't say that it's out of position by 14 arc minutes or 21 arc minutes. They know exactly, where the star is at. So the only way, within that coordinate system. So the only alternative is that the star's angular descent isn't following that, and it's lingering.
It's just a concept.
Yeah, it's just following a conceptual model.
There, weird atmospheric conditions that day. Like there's other things it could be. But anyway, sorry, I meant to not interrupt you too much this week. I'll shut up for a little while. And
no, you're
good,
good.
20 minutes.
You're good. But the in terms of experimental error, keep in mind that in every measurement, the arc length is the exact amount that corresponds to the time of occlusion, which corresponds to the proportional difference to half gamma, which is proportional to gamma. A lot of proportionals going on, but extremely significant. Let me see if I can pull up this diagram that Brian made of the difference between the conceptual model and what's measured. He plotted it out on a nice graph. See if I can find it. Oh, here it is, I think. Yep, copy link. Okay. So at these angles of occlusion or emergence, we can see here the dotted or the solid blue line is the perfect celestial sphere following the 15 degree per hour, 60 nautical mile per degree angular descent relationship. And then
The
at the
solid blue
time,
is basically globe but no refraction.
yes, correct. It's the celestial sphere model. And so like where these stars' true positions should be relative to their time of occlusion. And then here's where they're getting occluded at. So you can see that they're lingering beyond what the celestial sphere predicts in terms of true position descent, which is really interesting because, like I said, just using observation of the star alone, you would never know that this is going on because you're just referencing the true position. And just doing that, they have a correction here for you to reference the angular separation between this and the celestial sphere to link it back to give it usefulness for the ground position. So so yeah, that's
You should reiterate that. That's key. The simple fact is celestial refraction is incorporated in order to keep the usefulness of those stars GPs. It went in terms of like celestial navigation, etc. It has to be in there.
and like I'm saying, and like I said, I'm not saying that there's not refraction or something like that. But what I am saying is that for the coordinate system to maintain usefulness to that geocentric position that they start with, any optical apparent position that you reference has to be refracted from that true position by a specific amount to complete the symmetry of the coordinate system.
Depending on the observer height,
No,
above sea
depending on
level, and
no,
the angle
no,
of the star, right?
just the angle to the star, wherever wherever you
Well,
would
and
be.
your height though too. Like if you're at a lower sea level, like if you're at a, somewhere closer to sea level, you're gonna have way more celestial refraction being calculated in there, right?
That's what they say, but it ended up. I think it's just because you can see the stars uh, before they, you know, should on their model. So they just say that, this due to this much extra refraction or whatever, because like theoretically it would have to be, right? But if they're not following that 15 degree per hour ascent or descent rate, then it would just be the star is, coming into your field of view, and you're now able to perceive the light from it based off of its true position relative to you, which is angularly lower, but the apparent position ends up being visible before they predict. Okay, so when we keep going here, so anyway, I just wanted to show here that the amount of refraction this yielded, the amount of refraction failed to compensate by 435 meters of that mountain peak that it was supposed to be lifting up over, which is a huge geometric failure. And then Getaway Mountain here, we have 7 arc minute difference, globe off by 20. The full arc length was traversed when we referenced that. And let's see here. The refraction, really interesting. 3 arc minutes off of the full central angle, and almost twice as much as the drop over distance. And then over here we got Hound's Tooth. So Hound's Tooth was an emergence, and we predicted that the star would emerge a little later than it did, following the 15 degree per hour angular ascent. But it ended up emerging when it was 3 degrees in difference of that 15 degree per hour position relative to the rise over run of the peak. But again, referencing the central angles and the difference in air, it ends up, showing that the star wasn't following the 15 degree per hour relationship at the time of emergence, even at 10 degrees above the horizon there. The amount of astronomic refraction was overprescribed, so they prescribed 4, and there was 5 degrees of separation in the emergence. Or no, where was it? It was 4 degrees of astronomic refraction to 4 degrees of the central angle. Yeah, it was just
That's so crazy.
so it was just like basically trying to maintain a 1-to-1 relationship to that 60 nautical mile per degree.
Stay there real quick. Stay there. I just want people to understand this.
So
The refraction amount is almost equal to the arc length, which means that there really is no drop over distance
I
Yeah.
mean, the refracted globe prediction and the flat prediction are very similar in most of these, so it does make sense. The refraction equals about the drop, because they're clearly mostly offsetting for the results to be that close. Different prediction
And,
matching up so easily as well.
and so like what that implies though is that, the earth would be flat, and then you guys are just using a secondary correction to maintain usefulness to a coordinate system at that binds all the stars positions and angles at a specific time relative to an angular drop rate that doesn't actually occur in reality. That would be the outcome of that,
The
because
implication of it.
because like I
Yeah.
said, every angular band requires a specific amount of refraction regardless of what was ever actually measured, um, so that its true position will be relevant to its ground position.
Like if we didn't have other data sets, like if Celthia was the only way of measuring the shape of the Earth, like globe with refraction's a little closer than flat, but they are in the same ballpark.
Even
Um,
considering refraction in both models, the occlusion happens at the exact time. I mean, not or at the exact time that the arc length is traversed, creating the full difference of that arc length for both.
Sorry, do you have a flat with refraction number somewhere? I didn't see that on there.
Yeah, we're doing geometric intersections. Even if you applied any amount of refraction, it would be it would all that would be saying is like we're gonna change the time to a different time. That's
Well,
not
since you're measuring time, that seems important.
Yeah. And there's only one occlusion time, and that's the one
There's
we're
only
all
one
and
time
that's the
though.
one we're all
Yeah.
sticking with.
Yeah.
It's the one occlusion time is what makes this meaningful in terms of
It's
determining
like
what
not it's like
reality
not
is
not a
showing
s-
us.
not a single occlusion time matches the angular descent rate of 15 degrees per hour. And that's what the globe predicts, regardless
Yeah,
of
but
how these
Requires.
regardless of how these measurements um are going or whatever. Like, they're not following that descent rate. That's the important part of this. And there would be no way to ever know that, but just by internally referencing where's the position of the star, and then referencing the geocentric position and all that, because that's what makes it internally consistent, to give it a relative agreed upon ground position for all the stars.
And I would have got away with it too if it wasn't for that dang Dr. Mike.
But the globe model doesn't. I mean, globe model says that the descent rate pauses at the horizon anyway, right?
Not for the true positions, my good sir. And we're getting
Right, for the
intersections
apparent
that,
position.
yeah, and occlusions are a physical process between light source and uh, physical object. So the true position is the referenced light source. It's the source of the light that once was above someone's zenith, that is moving at 15 degrees per hour, and the apparent position is always the angular deviation from that true position, and it's angularly deviated by the amount of astronomical refraction per whatever angle you're looking at it is.
So what you're saying is left lane, the apparent position lingering or whatever, you're saying, oh, well, that's expected because of refraction. Well, if you're using a mountain peak, right, as the differentiator between, plane trig, spherical trig, and you incorporate that same level of refraction because it's linked to a coefficient that's linked to a certain angle that's linked to the known GP of said star, right? It's all has to be in conjunction with one another, but the occlusion timing shows otherwise. It shows that there is no angular descent of a star, right? Which is necessary in order for you to say that the stars are actually beneath my feet right now.
Yeah, no angular descent rate that they predict anyway. Because when
Almost
you
like the
do,
sky
because
and the heavens are above
when you don't see the
always.
star, I don't think anyone would contest that, they no longer see it anymore. But mathematically, you can represent that as negative coordinates, and that could be, beneath your feet, or that could just be out of your field of view, but still above you, moving at that same 15 degree per hour rate, because we know that the star is going to return to thereabouts to that position the next night, 24 hours later. So, moving on to Mount Blinn here, we have a rise over run to a peak of 1 degree 34 arc minutes. We have a drop over distance of 5 arc minutes here. So we have 1 degree 28 arc minutes for the glob peak there. And at the time of emergence here, there was an 18 arc minute intersection difference between the peak and the true position relative to the observer. For flat Earth, there was 12. But again, when we look at the arc length of this distance here, the star emerged 1 minute earlier than what flat Earth predicts for our angle, and it emerged 2 minutes later than what the globe would have predicted. And then with astronomical refraction accounting for that, if the true position has no relevance or anything like that, then the star would have already been visible 11 seconds ago because it already geometrically overcame the peak at that time. But that's not what occurred either. So again, looking at
You're
this
getting
too.
that from astronomical refraction being incorporated uh in terms of like that's the apparent position. It should have been already visible, the apparent position.
Yeah. Yep.
Gotcha.
And for the central angle fans out there, we got 12 arc minutes of central angle here. And we got 20 minutes of refraction. So like earlier when I was talking about, it's not following that descent rate, but it's still visible. This is like if there was no mountain there, they would be seeing this, like it is normally, and they would attribute the true position to being at 1 degrees 9 arc minutes relative to the observer, when in fact it was more closer to 1 degrees and 34 arc minutes relative to the observer for the true position. But the apparent position that you observe is 1 degree and 30 arc minutes. So it's coming into your field of view. So it hasn't angularly risen yet above the true position.
Which is a problem because because refraction's supposed to lift things up, right? Because of that astronomical refraction of 20 arc minutes, right? You should have already been seeing that star emerge from the mountaintop.
Then we got the same situation at a further mountain peak, or a same peak, longer distance here. So the central angle this time is 22 arc minutes, doubled the distance there. And then in this regard, we're 14 arc minutes off. The globe is 15 arc minutes off. It's predicted that there is 130 meters of drop over distance based off of the intersection differences of the triangle that we derive from that. We end up being 173 meters. The globe, when you derive based off of the true position at the time of occlusion for the observer, their amount, the difference of 103 or 304 and 173 is 131.
It's almost
So
it is the
so
same. Oh.
so again, relating that emergence to physically overcoming the rise over run to the peak, but just not at that angular descent rate, because the only thing that's at that intersection point on either side of the peak is an observer, and that's it. So then we got Goose's measurement here, Regulus, at 4 degrees over a central angle of 8 arc minutes. it gets occluded early by 31 seconds. And again, I think that's due to the relationship of the true position not following the apparent position. And if refraction had any role in it, I think that the central angle difference would be present in that.
So another question: have y'all observed this lack of 15 degrees per hour, or is it just worked out in your spreadsheet?
It's inferred from the occlusion timings at the difference of the time of occlusion at an expected angular descent rate. When it happens earlier, the only explanation would be, like logically, would be that the predicted angular descent rate isn't following what it should be.
And it needs to in the ball conception because the Earth's supposed to be rotating, and that's what's making the stars appear to go out of our field of view. It's because it's going beneath your feet.
So if I picked a star at my zenith at whatever time, early in the evening preferably, and then I tracked that star for 6 more hours until it disappeared, and I wouldn't get 15 degrees per hour.
So for the apparent position, as it gets lower to the horizon, it deviates from 15 degrees per hour. It actually starts deviating earlier than that, but you don't really
20,
notice it
yeah.
because it's a small amount. But as it gets lower, it starts deviating. So that's the apparent position you see is always the quote unquote astronomically refracted position. There's another position that's referenced that is following the 15 degree per hour relationship from when that star was once at your zenith, but that position you don't see. And that position is supposed to be angularly descending at the 15 degree per hour rate because it's supposed to be following the terrestrial sphere, and that's what makes the stars angularly descend at that rate. That's how they make the celestial and terrestrial sphere work together, by making the radius the same, because the celestial sphere has an infinite radius, but the terrestrial sphere, they say, has a 3959 radius, and that's what causes that angular descent of the star. So when they look at the star from that true position and reference 15 degrees per hour to it, they're also adding 15 degrees per hour with an angular descent that corresponds to 60 nautical
60
miles
nautical miles per
degree.
degree. Yeah.
for
That's the key.
for that position. And so what we're getting is when we're referencing where that position is at the time of occlusion, it ends up being off, but yet still an occlusion happened. And so if it's refracted, the globe predicts it would be above. Actually, it's pretty close in this one for astronomic. It's only 46 arc minutes. That's pretty, or arc seconds, sorry, that's pretty close. But in all other cases, it's at least 1 arc minute plus for being geometrically over it. So they predict that there's not an occlusion at that time, and then for the geometric intersection for the light source, they already missed that. And then for flat Earth, it hasn't occurred yet, following the 15 degree per hour rate, but it occurred anyway when it got to the end of that peak following 15 degrees per hour. So the same time interval, just different angular descent amounts. So, all right. Any questions or comments on that?
I want to hear from Dr. Mike. Are you available, Dr. Mike? I know you probably have some hustle and bustle going on.
I'm gonna go fill up my water. I'll be right back. You got it, Beast?
Yeah.
I just swung down my microphone. Can you hear me?
Yes, sir.
I think Alan did an amazing analysis of this, and I agree with everything he said.
Perfect. Is there so if you had to summarize in maybe like 2 or 3 sentences about the implications of of what was discussed here, what would the implications be?
The implications are something that was theorized early on, is that the appearance of a globe Earth exists only in refraction corrections. And when you look at real measurements, they don't agree with what globe Earth is predicting. And that's why the grand experiment that Theo failed to refute the null hypothesis, because if the Earth were a globe, it should have been easy to refute that we weren't getting flat Earth measurements, and yet from the very beginning, we were getting flat Earth measurements. And then as we dug more and more into all the various objections coming from different directions, it became real apparent that the central angle is explaining what's going on, and that when you take a globe Earth measurement and compare it to a flat Earth measurement of the same peak, including the same star, it's always off by the central angle. When you're using, that's when you're comparing uncorrected measurements. But all our globe Earth friends do is add refraction to come up with what they believe the measurements to be. We've all figured out that the refraction measurements, as these spreadsheets show, are just all over the place and they don't agree. And but what is consistent on the measurement, whether it's made from the observer's location or the peak, is that the difference is always the central angle. And that can only be true. I think Alan stated it this way: that can only be true on a flat Earth. A globe Earth could not behave that way, because the drop over distance expected from a globe Earth would mess up the measurement, but that's not happening.
Right.
We agreed before though that the only difference between the two models is the drop over distance, which is the central angle. So like it's not a surprise that is going to be the difference between the two, right?
Right, but it would be the difference on us being off by that amount and you guys would be correct by that amount. So like the intersection difference here for us would be 11 and then for you guys it would be 2.
Yeah,
You
it should
know.
be reversed.
And technically, it would even be it wouldn't even be 2, it would be 0 because it would be, if your model were true, then it would be following that 15 degree per hour descent rate exactly, and it would have occluded exactly when it hit the peak at 217 traverse on its way down to that arc length before it finishes it, because it would have already been at that angle.
Yeah, but I mean, like your observations say, once you include refraction.
Right, but that didn't happen or affect the measurement. Like as Mike said,
Hence why. Sorry, go ahead.
like the globe exists as a refraction correction. So, like the linear relationship of 60 nautical miles per degree only exists as an apparent model for a certain angular band, and the actual descent rate of the stars doesn't even follow that rate. They linger. You can look at them here as measured by mountain peaks using the internally consistent coordinate system.
Oh, well, the band again was the 30 degrees to 90.
No, it's like 30 to 70, something like that.
20 to 70 or something like that. Yeah.
And then not above 70.
Nope.
Well, the deviation from that doesn't, the deviation from the 15 degrees per hour from 90 to 70 is very, very small. So like as you go from like sub 70 to like, 30, 40 or 40, 30, that's where you start to get the, increasing deviations, and then lower than that, it increases. So,
But it sounded
It's
like
not
you're
linear,
saying,
basically, in those ranges. Sorry, go ahead.
no,
Go ahead.
it just,
Yeah.
I don't, that seems,
well,
I haven't looked into it, but that seems like it's probably not true.
Well, I
What?
mean, you could go into Stellarium and pick just pick a random star, and then look at the refraction correction when it's you know, 2 to 3 arc minutes below the horizon, and then rewind it back so that it goes up to, like, you know, as high as it'll go for that observer, and look at how the refraction corrections change per 10 degrees of refraction. And actually, there's a I can pull up this manual here.
Well, to be clear, I'm not talking about at the horizon. I believe that's true. It seems like it's when you get up to 30, I would assume it's 30 degrees all the way up. I'd never heard there was also a correction when you got near zenith.
No, when you're at zenith, there's the least amount of corrections that apply, and that's actually the position that they, you know, take for the reference for the true position to add 15 degrees per hour to, because it would be theoretically the most closely aligned position to wherever the light source of that star is, whether it be, you know, 60 billion light years away or what have you, or closer. But in any case, that would be the spot where it's the least amount refracted to use for a reference, and that's what they did. So let me see.
Yeah, so then the 1 degree per 60 nautical miles would work from there, I'm assuming, all the way down to get near the horizon, right?
No, I'm saying every 10 degrees of elevation band, there's a different amount of refraction that's applied to keep that angular amount good for celestial navigation to relate the true position. And it's
Out
between
of curiosity, have you ever done the calculations for, like, if you're saying this is all BS, the globe theory uses to hide the flatness? Have you ever done calculations for what sort of effects you'd expect from flat over long distances? Because, like, over these shorter distances that you can actually see observations, the difference aren't too big. But if you're looking at Polaris as you go down towards the equator, like, what? Have you ever done the math for that?
Come again?
So I'm just thinking, like, we know the ground position of Polaris. For simplicity, let's say North Pole. A little off, but close enough. And as you go down towards the equator, it gets lower and lower in the sky, obviously. So if you're saying that, like, these refraction corrections, all this stuff is just fake BS stuff globers have made up to hide the flat reality. And we shouldn't do any of that. We shouldn't think about it that way. Have you done the calculations based on just ignoring all the globe theory stuff, all the celestial fraction, all that? Just throw all that away, do it from scratch with something that is nice, simple, easy, like Polaris, and
Yeah.
figure out where it should be in the sky given the distance to the North Pole and the angle you see it at.
It would be whatever it is currently, because that's what it is currently.
Yeah,
And
but
that's
He's asking
and
if you've
the
done
and
the
the refraction
trigonometric.
correction, the refraction correction differences are exactly what is needed to make it useful at that 60 nautical mile rate when it doesn't follow that.
but I'm saying
So
your theory is
there's
it doesn't follow that. Those refraction corrections are BS, right? Correct me
you
if I'm wrong here.
you would never know, because all that's being referenced is the apparent position after you've seen after you have the zenith transit. So if you're assuming 50 nautical, if you're assuming that linear relationship and 15 and the and the angular descent of 15 degrees per hour, then there would be no difference in what you see. You would just explain the difference as refraction. So there's no way to calculate a different thing for what it truly is. That's just whatever optical effect. Like I think that the reason that that it doesn't obey that is a combination of refraction and the fact that our optics are non-Euclidean. So that's why I think that it doesn't deviate at that fixed angular 15 degree per
Agree.
hour descent rate. And that's all
But
that's
the,
all that's all that's needed, because when you say, like, you know, can you calculate the difference and stuff? Well, this mountain peak certainly tells the difference between the angular or between the true position descent rate and the apparent position that we see. So you could reference it that way, but I'm not even trying to do that. This doesn't serve any purpose.
I think his question might be leading to how on a flat Earth are you getting, say, Polaris on the horizon at the equator? How does that work on the flat Earth?
You remember those two quo que fallacy we were talking about, Geo? Remember? Just
Just
talking
No,
about that.
I just
it's
asked
just
a
optics.
legitimate question.
It's just optics. It's just how we see. We see in a sphere. As you get further away from things, as they get lower in the horizon, they get more compressed. They get angularly lower. It's just we see in a sphere.
Yeah, like nothing changed about your vision.
Check this out. Check this out. A lot of people are like, "Oh, the dome of vision, that's dog shit. You guys just made it up. Flat Earth's stupid, yada yada." This dome of vision is the same as this dome of vision that's used in this model where the globe is the globe shape instead of being on a different projection type. The apparent dome that we see in is true for both models. The linear drop rate and all of that is what's physically asserted for the globe, because that's what makes the coordinate system for them binding that GP to a specific spot on the ground. It's all predicated on a specific rate of descent and time.
Right, they're
So-
equivalent because they're
so-
both using the same projection.
Yeah, so nothing changes, and we all agree that when you use the coordinate system, that star will have a relative GP based on, you know, that 15 degree per hour angular descent rate and movement rate relative to the 60 nautical mile per degree relationship established for that interval of descent. That's what makes the symmetry of the coordinate system. Like, no one is contesting that, but you would never know the difference unless there was, I don't know, a mountain peak in between you and a star and you were calculating occlusion differences.
Right. Yeah, and I sent you a timestamped video. That guy is just kind of explaining the basics so people can kind of like visualize it.
Oh, nice. Is it yeah, we could play this out.
Just so for people to get a better
stars would
grasp
appear to
if
spin
you're not too familiar with celestial mechanics and stuff.
around a circle, and the axis of that circle at the zenith, the point overhead we talked about earlier. That point in the sky
sound's kinda
around
off.
which the stars
It sounds horrible. What's wrong with it?
I don't know. It's fine on my end.
It's like it's being staticky.
Maybe try now.
My question would be like, you say this,
Rotate.
that's just how we see. How do you know that's how we see?
There you go.
Because that's literally what we see.
It's how you see, bro. Curved visual space.
Yeah, we've looked at some research papers on that.
No, I've never seen a research paper that says that we see in the way that the personal azimuthal grid of vision says we see.
Promise you.
Oh, I got you. 1 second. We'll pull some up.
Yeah, okay, all right.
Hold on.
Get it.
Move on.
Not only is there research papers, but there's multiple from different scientists. I like Lunenburg. He's my favorite curved visual space guy.
Where do we
I was
start?
just like, all right, dude, just give me a sec. I got you.
All right. So earlier when we started, actually, you know what? Let's start with Umland first. So all observations are described as a hemisphere of vision and putting the observer in the center. That literally creates the azimuthal grid. That creates the 60 nautical mile per degree relationship. That's what merges the globe to the celestial sphere. So that's like hint number one that they're related. That's how they always describe it. So let's see here. Calculations from the celestial navigation always refer to the geocentric altitude of the body. The altitude when measured by a fictitious observer being on the plane of the celestial horizon at the center of the Earth, which coincides with the center of the celestial sphere. So literally mapping it to that to start us off with. Now we'll get into some descriptions from a book from, let's see, this was 1777. Oh, the same year the king made the royal decree to use his coordinate system. So this book is the grammar and situation and extents of all countries and histories and kingdoms of the world. Basically, this guy traveled to different kingdoms and asked them about their religion and navigation and cosmology, etc. So anyway, they talk about how in the Europeans, they're using this celestial sphere model and to describe the northern hemisphere and the southern hemisphere, and a spectator spanning the surface of the Earth can freely see half of the heavens, which seems to be above him, the other half being under the earth beneath him. Now the apparent plane or flat of the or on the flat hands, which is that they're not saying the Earth's flat here. They're just referencing the fundamental plane of the coordinate system, which is that geocentric position that they use. Yada yada goes on to talk about the celestial bodies. Later, we will chiefly find that there is a greater conviction of the subject of geography. Nope, that's not related. Okay,
You
and
can read
then
that right there, the horizon one.
we're at.
Now, if the apparent plane or flat which he stands on was conceived to be extended till it met the heavens, it would there be bounded apparently by a great circle called the horizon, which divides the visible from the invisible hemisphere.
Oh, thank you. There you go. Yeah, so there's clue number 2. Then we have a reference in 1892. This is Old and New Astronomy. This is some guy writing about astronomy or whatever, an old textbook. And he says, overhead is the dome of the heavens, which is as far determined by the actual position of the visible bodies, like the heavenly orbs or the blue sky or by the clouds, and as in reality has no definable shape, but which may be geometrically regarded as a hemisphere around O as a center. So if you were O here, the observer at the center, this is what you would be seeing. There's our fundamental plane, celestial sphere expanded outward from that. It is not intended that the natural idea of the observer, whom the dome of the heavens appears somewhat flattened form, the horizon being between 3 and 4 times as far away as the region overhead. In considering the cloudy sky, we must remember that if we were to rightly understand what we see, that usually the curved surface at which we look at is much flatter than it even is, or than this, we mistakenly attribute the dome shape of the heavens, whereas in reality, the curvature is no greater than the curvature of Earth itself, which under ordinary conditions is imperceptible. So we only see the curved part of the heavens. So when we go back to Oop, I just closed it out. Sorry about that. So when we go back to these references to conceptual models, the azimuthal dome of vision, this is what creates the graticule, the coordinate system that this projection is, that this observer is standing on and referencing. Same here. Same exact thing. We always are referencing the apparent, and I'll do one more to give some more context, just for good measure. Nope, let's debate thumbnails. I need this one, I think. All right. So if anyone needs references on curved visual space, I have several sections in my Zotero that I can export. But here is some leads. I highly recommend. Where's that one that Wagner? There's one by Wagner right here. The Geometries of Visual Space. This guy gives a detailed summary of like 15 different visual space theories that all cover like, where they experimentally fail, where they exceed, et cetera, because there doesn't seem to be one unifying way to describe optics in Euclidean spherical or hyperbolic geometry or anything like that. It seems to be a mix of a logarithmic scale where it's, dependent on different distances. It's dynamic as you get further away. It more scales like that where the effects change. So you can read more about that in any one of these, but I highly recommend starting with Wagner because he covers all the big ones and breaks it down pretty easy.
No, I think Wagner's one that Gleam shared, but that doesn't support the personal azimuthal grid of vision. That one's.
It supports.
If I remember right, that one's a personal. It's like a psychology paper on human perception, but we can take eyeballs out of it and capture things on a sensor and we don't have to worry about all that, human brain.
It's literally a book explaining how we don't see in Euclidean parallel lines and things converge at the horizon, etc. That's what all these.
Well, do you think that's true of a camera?
Listen, is it true in reality that when you're looking at train tracks, they appear to converge, but they don't actually? That's all you really need to know. We're not.
Yeah, but that's not curved visual space. That's just perspective.
the whole.
That's curved visual space, dude.
No, it's
Sorry.
not.
Okay.
Like train tracks converging is not curved visual space.
All right. So 1 second, dude. We're gonna go to.
What do you think perspective means?
Hold on, dog.
Perspective is just it's straight light rays converging, and there's basic math that will predict like
Now all the light
how
rays
things
are
project.
straight.
Yeah, they're not converging in a Euclidean apparent at the infinity position or whatever. There's whole studies on all of that, and that guy that you tried to say was doing like a psychology experiment on perception. It's literally about mapping things in three-dimensional space versus where you perceive them based on that deviation. And does that deviation follow a hyperbolic negative curvature? Does it follow spherical curvature? What type of, this is what these people where theories were about, and that's what that dude's book summarizes. And you would know that if you actually read it instead of trying.
No,
to
you just agreed with me. You said his book's about human perception. They basically set people up. These are all short distance things, by the way. And they would set people up and they'd say like how far, like turn, like stand straight, turn sideways, look over your shoulders, and tell us like how far away do you think that stick is, or which way is it pointing? Hold on. And then they would say, okay, how far off was that person from where that thing actually is? And then they would map those, and they found that people do have they consistently misjudge distances.
Right. Why is the term 20/20 vision used?
1 second.
I'll wait.
So 1 second. If they misjudge things closely, right, physical objects, what would you think that would mean for objects in the sky? And then number two, how you perceive things is literally how, like that rate of change is literally how the graticule is made, establishing that 69-mile nautical relationship. So it's literally based on how you perceive the sky. Trying to change the terminology doesn't make it a different conversation. You still see in that exact same way. And I'm about to pull up.
Well, so to your first question, I think you asked a question. Can I answer it?
Yeah, go ahead.
Or okay. You said if it's bad for things that are close, how is it for things that are far? I don't know. Honestly, it might be bad, but my guess is if you took people outside and you showed them Polaris and you said, what angle is that? And you just had them guess it. That I imagine people would probably be off. But if we went out and we set up a camera that was leveled, for example, with basically known specs, it's going to be pretty, like, extremely close. Right, at finding the actual, like if you got a Theodolite, a camera, it's gonna be correct. That's my point about, like, I think when you mix human perception in, like it muddies the waters.
Yeah, it's still gonna be a factor, and everything that is based off of like the literal positions of the stars as you perceive them is what supposedly defines the globe. So anyway, here's another left and right eye. This is called a Mueller circle. This is a theory describing optics and the non-linear change in position over distance for objects as seen by an observer. What he describes this as you take a circle, slice both eyes in half, and then rotate the circle 360 degrees. It creates this latitude longitude grid that we're looking at here. So as things are closer, they're not separated as much. There's not that deviation from where they're actually at in 3D space, versus when they get out here, there's a different amount of separation there, showing the exact same conceptualization. And then I got one more quote that I'm looking for from Lundberg. It should be up here at the top. Yeah. Okay. So this is Lundberg saying, talking about the visual field and the spatial field, and because it's asserted in mainstream optics that we see in Euclidean vision and all that, but he gives the example here of how the sun and the stars are great astronomical bodies, but the sun we see at only 0.5 degrees angular size, and the other celestial bodies are like a couple of arc minutes in size. So he's saying that the only way that can happen is if there was a deviation from seeing in 3D Euclidean geometry. So
I'll Can I read it real quick?
Yeah,
Right
go ahead.
there. Okay. It says, however, we cannot be sure that the map truly represent the sense qualities of form and localization of objects. This would be the case if the apparent distance of any two sensed points were always proportional to the geometrical distance of the associated points of the Euclidean map. Clearly, this is not true. Astronomical objects like the sun or the moon are seen at finite distances. Their sensed size is also finite and in no way proportional to astronomical dimensions. Even the sky itself gives the impression of a dome of finite radius. There you go.
Yeah.
I mean, I can keep going
No,
if you want.
you're good. It's a well studied thing in how we perceive things, and then uh that's basically the back, and then you get into like the studies of alley experiments and stuff, which are closer. But the main point of those is that if we saw in Euclidean geometry that when they plot out the errors in their measurements for the people and where they perceive things, the x and y axes should never intersect when they plot those out, and they always do. So the implication is that they're not seeing in parallel lines. So anyway, the big takeaway from that, though, is that in both models, we're using our vision to construct a map. And in this case, the globe lads have solidified a specific angular descent rate and built everything, time synchronized on that. And as so long as everyone agrees to use that coordinate system, then the apparent ground position as defined by the exactitude of the 15 degree per hour angular descent will be accurate for people to use because they're all using the same system. Whether or not that ground position actually exists at that time or not for the observer doesn't matter, because they're referencing that internally in the coordinate system, and it's going to work, it's going to be symmetrical, and it's going to give you the correct reference for where the star would be at that time.
Yep.
I don't feel like it was. I don't feel like you like addressed the question. I mean, we kind of like wandered into different areas, but I do agree that we perceive the sky as a dome of finite radius. I believe. I mean, that seems apparent. What I was getting at was the idea that this dome is that we live on a flat plane, and that the stars, as they move through the sky, they move at like we would expect them to move according to normal perspective, which means that the further away they get, the slower that they would drop. Whereas what we see in reality is a linear drop. That part, that's the azimuthal grid has other things with like azimuths shifting, but that's the big thing that I feel like it's an assertion you guys make that's not, it doesn't feel very.
We don't see a linear
justified.
drop though.
I was gonna say, yeah, we don't see a linear drop,
That's why they have these extreme corrections to make the apparent position still tied to the ground position that's moving at 15 degrees per hour.
Well, like at 70 degrees, what's the correction? What's the correction at 70 degrees?
Almost nothing.
Very minimal.
That's
very minimal.
my premise, Pinky. Have you been listening?
No, I've been listening. I've been listening. What I think is like you're communicating it so that.
So listen.
I have been listening. Yes.
You have been listening. So I said there's a linear band which they use and assume that is the fixed angular descent rate within that band for the 15 degree per hour relationship. As things get closer, there's a deviation. Now it's assumed that deviation is only the apparent position in the globe model. I'm saying that these cell-theo measurements, the reason that they include earlier is because the angular relationship isn't even being followed, or that 15 degree per hour descent rate for the true position isn't even being followed. That's what I'm saying.
Yeah, it's probably not. We're probably off track with it, but I feel like you're sort of like brushing over the 30 to 70, where basically there's no correction, and yet the sky's behaving in a way that is not what we would see with perspective.
That's exactly what we would see.
That's about half a degree. Like, you're not talking about massive. Like, you phrase it like it's a massive correction, but it's about half a degree at the horizon. These are not large corrections.
There's the least amount of angular separation when it's directly above you. Of course, that's a linear portion. That's what we're saying.
Yeah.
That it's non-linear. That's what, like, when I was going over the where's that Vith Mueller torus at? Shit.
All the
Well,
way
anyway,
from zenith
anyway,
to horizon. Half a degree.
anyway, it doesn't follow that linear relationship, and that's the purpose of these corrections.
Correct. And this is why, if you look at any celestial navigation, guide or article or anything like that, or any nautical almanac, in terms of stars to use, they only use stars that are in that band.
Yeah, like they're
So-
above 30 degrees, right?
Yeah, they
there's a
have
reason for that.
Exactly.
We know,
We
but
understand
there's a specific that, and we're saying that coordinate system establishes internal consistency based off of the apparent position, and assuming that the light source also is following that 15 degree per hour angular relationship. And we're saying they're not. That's not what's happening. And as you get into the lower elevation bands, they start applying formulaic corrections that have to model fit, because if it's not the correct amount, then the star's ground position has no physical meaning in the coordinate system. That's all we're saying about the refraction thing.
Curve fit formula. That's what we've been saying for 30 presentations.
And then we got on to optics and how that works. And we
play that
we
play
don't
that little
predict.
video for people.
I will, 1 second.
No one
Video
addressed
explained
my 2020 comment earlier.
All right, give me a second.
Get to that.
We're gonna play out this video real quick. I'm gonna put it at 1x or whatever.
Is the
Fine.
celestial pole. Of course, you likely won't ever see that because no one lives at the North Pole. So as we move downwards in latitude in the northern hemisphere, that point in the sky around which the stars rotate will move down towards the north part of the horizon. If you're in the upper latitudes, it will appear higher in the sky. The nearer you are to the equator, the closer that point is going to be to the northern horizon. If you've ever looked at a globe with latitude and longitude lines on it, you can probably imagine pretty easily our next set of markings in the sky, the celestial sphere. To locate objects in the sky, we use coordinates like on Earth, but instead of latitude and longitude, we project those lines out into space as if they were on a transparent sphere surrounding Earth. And these are called right ascension and declination. Right ascension is actually easy to remember. If you face north and the sun rises in the east, which side of your body is that on? Well, it's on the right side. So the sun ascends from your right, or right ascension. These are like the longitude lines on Earth that start at one pole and run to the other pole in equal spacings. Now in right ascension, they're listed in hours and minutes, and the 0 hour for right ascension begins in Aries the Ram, which is a zodiac constellation. Easy enough, right?
First point of
And
Aries.
declination is simply the number of degrees away from the celestial poles. So the degrees from the celestial pole to the celestial equator is 90 degrees, the equator itself being 0, just like the degrees from our North Pole to our equator on Earth. With me so far? Great. So let's review these quickly. North, east, southwest never change, of course. The meridian splits the sky in two halves from north to south. The zenith is directly overhead. The ecliptic is the path the sun takes in the sky, along which the planets largely appear to follow. The celestial pole is the spot in the sky around which the stars appear to rotate as the Earth spins. The celestial sphere uses similar coordinates as longitude and latitude, but are called right ascension and declination. Not hard at all, right? Okay, right ascension and declination may take a bit getting used to,
There you go.
but the rest should be pretty straightforward. In the next video, I'll explain how to understand the difference between brightness of objects in the sky.
Pretty little good summary on it. So longitude and latitude, right? Longitude, right ascension. Latitude, declination.
Thank you, sir.
Yep.
Really useful for
I have one more question,
understanding
then
the celestial
I'll
and
drop off.
terrestrial spheres. Yes, go ahead.
So because I think most of these mountain ones, just by nature of being further away from the mountain, they're going to tend to be really close to the horizon. I've been doing some. I have a program I'm writing to evaluate some of the eclipse data. I'm curious what you think will happen when we do the eclipse stuff up, because most of those are going to be up above 30 degrees. So refraction is going to be, I would say more or less a non-issue. Do you think that will hold true that the
It's a little different subject, but if you want to tackle it,
yeah,
Alan.
Brian has it plotted out on one of the things in the what do you call it, in the
Yeah,
PDF.
just type in eclipses.
Yeah, the PDF.
Yeah, let me see here. Brian eclipses.
There you go.
Let's see that one. Right here.
It's like near the bottom almost. Oh, there it is. Yeah.
Here you go. I think this was the comparison and deviation. So they're pretty close, you know, following, right? Or I think it started at 70. Yeah, right here. So they're pretty close right here. And then they start to deviate as time goes on. So as the angle
Phantom,
gets
you're
lower,
echoing.
yeah, you're echoing. You can see the deviation right here.
Yeah. So what do you think causes that deviation?
Optics. It's just how we perceive it.
Yeah. The thing that's
Well, no, like what? Like if we looked at five different eclipses, when
hold on one second. There you go.
Yeah, say we looked at 5 different eclipses. Where like would it always be on the ends that it would diverge? Is it when the eclipse is on the horizon?
I would assume so. I would assume it would look very similar to this.
Cool. That's it for me.
Alrighty. And then let's see, Killen, or what was your Clint had a question. Rob on
crap,
the
I've been
level.
watching chat.
No, it's Rob on the level. You had a question.
Rob's running to his mic. He's out of breath.
I'll give him a couple of seconds here.
Yeah,
we're gonna.
You asked about 20/20 vision, and to answer his question, that means if you've got 20/20 vision, you see at 20 feet what a normal vision person sees at 20 feet. That's all that means.
Yeah, like
I think there's more to it than that, left lane. I think if you asked an optometrist, we'd get a different answer. Don't worry, I'll Google it myself.
I don't
Well, that's
disagree
what
with
my
what he said.
optometrist told me, so I don't know.
Yeah, I don't
That's what my
necessarily
optometrist told me as well.
disagree. Yeah. I think it's related to like when they give you the test to see if you can resolve the letters. It's like your ability to resolve things at a distance, right? So, all right, if that's it, we're gonna go ahead and wrap up for the year, lads and ladettes. Next time I see you boys, it'll be an entirely new year.
Oh man, so quick.
Thanks,
oh wait,
Alan.
Rob's here. Oh, Rob, did you have a quick question? You said.
Well, I did, but left lane tried to answer it with something he says his optometrist told him. Why we use the term?
2020.
Yeah, why we use the term 20/20 vision when dealing with optics?
Because the
Oh,
standard
wait,
for, an eye
lads.
test is 20 feet away from the thing.
Yeah.
Marks on 20 feet away, and have a standard of what the average person can see is how well they see it at 20 feet. If they see it, if they are 20 feet away, but they see it as well as a normal person sees it from 100 feet away, they have 2100 vision. It's pretty bad. They see it
By
as
the
well
way-
as, a normal person sees it from 10 feet. They got really good vision, 2010. That's all.
Tagged you, Aceldius. I can't pronounce your name. I'm sorry.
I'll say
Tagged you and Pinky with that book. The entire Geometries of Visual Space. That way, there's no confusion next time. Not saying from you.
I don't.
Aceldius.
I'm in the middle of moving house, but I'm
Can you tag me in that too, please?
Yeah.
Thank you, Gally.
Not Galley, but okay.
Feast to go, sorry.
Shout out
My
to
bad. At
Gally,
least I
though.
can call you Tora.
Hey, Alan, can I ask something real quick? So at the end of the day, like in a way, does this come down to like star drop versus they're claiming the actual ground or the earth itself is dropping, but actually what's really only happening is just star drop, essentially.
Yep, essentially. It's just star drop, and not even at the rate that they
Not
predict.
even star drop.
Yeah.
It's just moving away.
Yeah,
Yeah,
it fits with
essentially.
the planar geometries.
Yeah.
Yep.
What if we thought of the sky as flat also?
Well, the celestial sphere is a sphere of
Dun-dun.
infinite radius, and that is technically flat. So,
Sphere of infinite radius is flat.
touche.
Thank you, gentlemen.
All right,
Yep,
lads.
and the only thing that links them together is that, 60 nautical miles per degree. That's based off of the radius value. That's the only thing that links them together. But anyway, sorry, continue.
Yep. Just we will catch you guys on the next one. We're gonna try and get some repeat measurements at Getaway Mountain when it clears up a little bit. And I heard Cyrus is also looking to get some measures in. And Gio, I heard you were gonna get some measures in as well. Is that true? Confirm?
Well, it came up the other day, actually. Bull Knight was posting the link and talking about the Sell Theo bounty, and he was
Yeah.
bringing it up. I was just saying, I was outside looking at the sun, and I live in a very mountainous region. So I said, I was like, wow, the mountains out here. And then Bull Knight was like, oh, you should do a Sell Theo measurement. And we started thinking about it. The thing is, the mountains that are right near me are much closer, though. So I would have to probably get up at some other altitude and even see what I could see. Yeah.
We want all angles because we want to see the difference in true and apparent position for them. We want it all. Like if you any angle and distance is good, even if it's not going to show like Earth curvature significance, it'll still be significant in the deviation for the celestial sphere, which is based on their true position. So it'll still be good.
Yeah, so Bull Knight had kind of brought it up, and then I was talking about the mountains around me, and then Cyrus came in, and he got sparked and like interested.
Nice.
Yeah, so dude, he just instantly went to it, and he has I think he said he has a P900, P950, and he also has like a different camera as well, like the DSLR one. So that one is what he was, and he came in I think like last night, and he was like, "Does anyone know about camera settings?" And he basically, the ISO and all the settings to get it. And yeah, and then he was gonna do it, but it was like really windy, so he was more just kind of getting everything set up. But we did it on the live stream a day or two ago, where we pulled up Peak Finder. We compared it to Google Maps and all of the his coordinates. We did it all live on here.
Nice.
So yeah,
Selfie with the boys.
Yeah, and then we were trying to find like pretty much one of the longer ones because he was attracted to that, and I was mentioning how potentially in the desert, because it's more dry and the unique conditions, he might be at a place where he can get one of these really long rangers, because that's my understanding. Like even like sunsets in the desert, sometimes they can just fade to a tiny little dot because it's so dry and you can see the sun for so far, just because of the environment, like less moisture. And it does seem like that's the case. I mean, this one, if the furthest might be about 170 kilometers. It seems like if he got up on the other mountain, even without that though, like 150. And the thing is, he can see it with his naked eye, so it's pretty clear. And then the camera, like, yeah, you saw the preliminary pictures. Isn't that one of the most like kind of? It just looks really like it's going to be amazing. It looks incredible in terms of the detail and the distance that it potentially is going to be.
Yeah, I can't wait to see some stars hitting that bad boy.
Great presentation, Alan.
Yep.
Catch you guys later. I gotta make some calls.
Yeah, I'll pull up Cyrus's screenshot real quick.
Oh, really? Ooh, let me see this real quick.
Yeah, take a quick gandy. Now, obviously, we will be playing Mega Bonk later. So.
Wow.
It's called Granite Peak.
That's a peak, right? Dude. Woo! Yeah, that's
I think that's the one from that's the one from ground level, and then there's another. So there's actually like Granite Mountain and Granite Peak, and ironically, one of them is in his east and one of them is in his west. So it's like there's two that are both called Granite, but one's the mountain and one's the peak, and that one's the peak. So he could go potentially up on the Granite Mountain and look at the peak, which would be at a much higher altitude.
Dude,
well, somewhat higher altitude, and then from a further distance too. Yeah, so kind of get a higher peak from it there, because right there it's like a little bit behind that. It's basically in the middle, like that hump right in the middle.
Right there.
Just kind of
Middle.
You know what would be
Yeah,
crazy
about-
to get this bad boy over here.
yeah. That one looks because that one even might because it might be further.
Yeah, that one's hella far.
Yeah, it looks like it's on a whole back layer. Yeah. Yeah, but the granite one is the like pretty much dead center. Yeah, like yeah, right there. Yeah. That's
Yeah, there's lots of good potential here. Can't wait to see what happens. So yeah, quick recap before we wrap up. There's the Celestial Theodolite Rewards Program. The link is in the chat there. But basically, if you live in the southern hemisphere right now, if you take a celestial theodolite measurement that's sub 128 kilometers, you'll get $100. If you have one that's over that, you get $200. In the northern hemisphere, you get $50 per peak, and if it's over 128 kilometers, you get $100. We have a current prize pool of $500. It's first come, first serve. So get those in while supplies last, as they say. And then here's how to contact me, contact information, and upload the information. And all you need is your observer location, latitude, longitude coordinates, the target peak name. So if you can look that up on Peak Finder, and then we can get the lati and longi of that later. But we need to know the peak, and then the timing information. So we need to know when you started your recording of the star occlusion. So your device needs to be synchronized with GPS time, and if you can have it so that either a thumbnail or either a timestamp is displayed in the video, or if the file name when you create the file is based off of the current time, based off of whatever GPS time it's synced to, that would be super useful. That's all you need to do to make a successful measurement there. And then the quality, in terms of quality, you need to be able to define the peak. You need to be able to see the star. So if you can get something that looks about like this, could be a little worse, could be a little better. Doesn't matter. If you can get something around this range, you're good to go, as long as it's definable. If you're having trouble with the peak at night, you can record a little like at sunset and get the silhouette, and then reference that recording later, as long as you don't move the device. All right, that is everything. I'll see you guys next year.